This is the Module 13 R video. So in this video, we're going to look at how to use R to perform some different hypothesis tests. So as usual, whenever we start one of these videos, I've got my folder opened up here, and I want to make sure that I've got all the files that I need handy. So we always want to make sure that we have our code book available. For this video, we're also going to need the 13.3 R notes, as well as we want to make sure we've got that Module 13 R script. So I've got everything here. I'm going to go ahead and open up my R script. All right, so here is the script. But before we take a look at this, let's look at the note set that goes along with it. So here's our note set. So again, we're going to look at, oh, and that is a mistake right there. That should say several different hypothesis tests, not confidence intervals. So I'll have that fixed in your note set. And what we're going to look at here is how to perform different hypothesis tests. Now, keeping in mind that we're only going to look at a select few here, there are many, many more hypothesis tests that are available. So we're going to start out by looking at the one sample proportion z-test, and we're going to do these all in context of your BRFSS dataset. So one research question that I might have from my data set is, at the 5% significance level, is the percentage of people living in Kentucky during the year 2018 receiving a flu vaccine less than 50%? Now, part of the reason I've got that 5% significance level there, that's what's denoting my alpha. And remember, you can think of that as there's always potential error in a hypothesis test. So we want to include that information because that is acknowledging that there's always that potential for error. So what we're going to do is we're going to look at some R code and see how we could perform this particular hypothesis test. All right, going to RStudio. What we've got here is our Module 13 R code. So as always, the very first thing that I'm going to need to do is I need to read in my data set. So here's the code to do that. And my data set has been read in. All right, so we're going to look at how to perform that one sample proportion z-test. And what you're going to find out is this is very similar to when you calculated the confidence interval for a single proportion in Module 12. So the very first thing we're going to do is we always want to explore that that variable that it is we're performing the hypothesis test on. So in this particular case, I'm looking at that flu shot 6 variable. So I'm just going to look at a table of this variable to get a feel for what's going on. All right, so for this particular variable, here is my table, remembering that the 1, the 2, and the 7 represent different things. So I'm going to go to my code book, find my variable. All right, so here's my variable. So I see that the 1s are my yeses, the 2s are my nos, the 7s are the don't knows, and if I had any 9s, those would be the refusals. All right. So the next thing I can do is I can actually jump right in and perform my hypothesis test. Now, in order to do this, this is very similar to when we looked at the confidence intervals. I have to decide, what is the outcome I'm interested in? And so in this case, it's going to be the yeses. And then from there, I have to make the decision of what am I comparing the yeses to. So I've made the decision to compare the yeses to everything else. You could reasonably make the decision to only compare it to the nos, which would slightly change the values here. No matter what you decide, you just have to make sure that you include that documentation so that someone reading your report knows, okay, this is how they perform that test. So here what I've got in my N is going to be the sum of all of the values that are not in A. In other words, this is telling me the total number of observations. K here is going to tell me the total number of yeses. We're going to use the prop.test function, and if you'll remember, we saw this one when we went to calculate our confidence intervals in Module 12. Down at the bottom, if I do question mark prop.test, I can read a little bit more about this particular function. So notice I've put in here K, N, and then I've added in this alternative equals less. Now, the reason I'm doing this is my hypothesis test is looking to see if that proportion is less than 50%. So it's a one-tailed test, and I need to tell R what direction we're going to be going. And so it's going to be the left tail test, or in the alternative, I have a less than sign. Now the next thing you might say is, well, you're checking to see if it's less than 50%. How does R know that it's less than 50%? Well, by default, this particular function what it does is the default value under the null is going to be 50%, and that's a common value when we're looking at a single proportion, but you can change this. So notice here, if we look at the documentation, it has this p is equal to null, and if we look down here, p is the vector of probabilities of success. Here's where you can change that, and you could put in a different value. All right, so let's run this and look at our output. All right, so here is our output. Notice here, this is the same output that we got when we looked at the confidence interval. Now, there are some parts of this I ignored when we talked about the confidence interval, and so now that we've seen this before, I want to talk about some of these different pieces. First of all, notice up at the top it says one sample proportions test with continuity correction. Now, for many different hypothesis tests, when you run them in software, there are different corrections that can help if certain assumptions aren't satisfied, or they're corrections that are just recommended in general. This particular continuity correction, we can actually read about it here in our documentation. If you scroll through here, it will talk about the correction. Here it is right here, correct a logical indicating whether Yates continuity correction should be applied where possible. So in general, they are recommending to always apply this correction. So I've ran it with the correction. There are some other people that say, hey, you should never use this correction. And you'll find that a lot when you really dig into statistical analysis. There's not always a consensus on how to perform different tests and whether corrections are needed. So you just want to make sure that you do something reasonable and document what you did do. So I've left this with the correction on. You could put correct equals false in here to take the correction off. That would be up to your discretion as the person running the data analysis. Now looking here, notice it's got data, k out of n, and then null probability of 0.5. And again, we already wanted 0.5, so I didn't need to change anything. Now, if you'll remember from module 13.2, we said there was going to be a z statistic with this particular test. Well, it ends up that R reports it as a chi-square test statistic. If you take a z test statistic and you square it, that ends up becoming a chi-squared. And so this is actually the exact same test, it's just reported a little bit differently. And you'll see that through different sources of information, you'll have the same thing that's reported slightly differently. So that is our test statistic, and that is our p-value. And then they tell us under our alternative, we've got p less than 0.5, which is exactly what we wanted. So if we go back to our note set, notice I've highlighted that important piece where we get our test statistic and our p-value. I've noted here in the data, I considered those responding no, don't know, or refused as the complement of yes. Again, you could have just done the no's, and then you would need to report that. So in conclusion, since our p-value is very small here, at the 5% significance level, we do have evidence that less than half of Kentuckians received a flu vaccine in the year 2018. All right, let's look at our next one. So we're going to look at performing the binomial exact test. And if you'll remember, the hypotheses for the binomial, or the one sample proportion binomial exact test, and that of the single proportion test that we just looked at are exactly the same. The difference is that the binomial exact test is very useful for when we haven't met that sample size assumption. So if we were performing this and it ended up, we didn't meet our sample size requirement, we could always go and do the binomial exact test, which is a better choice. So for here in the code, I'm just showing you how to do this for illustration. No, for this particular example, our sample is massive, so we don't actually need this test. So really the only difference we need to do is, instead of using prop.test or proportion.test, we're to use binom.test. And so we can run this. And notice we'll get some similar output. Up at the top it will say binomial exact test. I have that copied here in the notes. So here it's going to report our p-value, again very small. So using this test also, we find at the 5% significance level we have evidence that less than half of Kentuckians received a flu vaccine in the year 2018. Let's look at another example. So here we're going to look at a hypothesis test for a difference in proportions. So now suppose my research question is, at the 5% significance level, is there a difference in the proportion of people living in Kentucky with good, better health who received the flu vaccine compared to the proportion of people living in Kentucky with fair, poor health who received the flu vaccine during the year 2018? So again, notice this is very similar to what we did when we looked at confidence intervals. And so we can use our data set here to perform this hypothesis test. All right, so looking at our hypothesis test, what we're going to do is very similar to what we did when we constructed the confidence intervals. So I'm going to first create two objects, one to store the flu data for those with good, better health, and another to store the flu data for those with fair or poor health. And so I've done that here. And then we can look at a table in the code book to see that there are 4 possible responses. So let's look at the table for good and poor. So looking at good, better health, we see that we had in the good health or better good health category, we had 1,876 people who received the flu shot, 2,829 who did not, and then those 11 who didn't know. And we see something similar looking at the table for those with the poor or fair health. All right, so now to perform the hypothesis test, again, we're pretty much going to do the exact same thing that we did for the confidence intervals. I'm going to find the number of successes in the good group or the number of yeses in the good group compared to everyone else in that group. And same thing for the fair poor health group. And again, I'm going to use the prop test. So running this. So again, this code looks almost exactly the same as what we saw for the confidence intervals. It's just now in the output, instead of using the confidence interval portion, we're going to use the hypothesis test portion, which is given right here. So going back, here is that copy and pasted, and you'll notice here we have a small p-value. I've made a note about my data, what I'm considering to be the complement of the yeses. And so here at the 5% significance level, we have enough evidence to prove that the percentage of people living in Kentucky with good, better health who received the flu vaccine differs from the proportion of people living in Kentucky with fair, poor health who received the flu vaccine during the year 2018. And one thing to notice here is in my alternative, we did have that two-tailed test. I was testing to see if those two proportions differed from one another. Going back to the code, if I wanted to prove that one of them was less than or greater than, just like here where we added in this alternative statement, we could do the same thing here in this hypothesis test. All right, our last example we're going to look at is the chi-square test of independence. So now we're going to ask the research question, is there sufficient evidence at the alpha equals 0.05 level to conclude that a person's health status is not independent of whether or not they receive a flu vaccine? So again, we can use the code. And you're going to find I did something very similar to what we did for the previous hypothesis test. I've created objects, one to store the good health and one to store the poor health flu data, looking at a table of each of them. And you'll see this is the same tables that we had before. So now what I have to do in order to perform the chi-square test is I actually need to build the contingency table in order to do this. So here what I'm going to do is I'm going to create a contingency table for my two dichotomous variables, and here's how I'm going to consider them. My first dichotomous variable for health will be either you were in the good, better health, or you had some other status. And so that other status can include the poor, bad, the don't know, and the refused. And then for my flu status, my flu vaccine status, I'm either going to have yes, you received the shot, or you're in the other category, where the other category, again, is either you didn't receive the shot, or the vaccine, I should say, you don't know if you did, or you refuse to answer. And so that's what this is doing, this chunk of code right here. So looking at the individual lines, first I'm doing this for the health variable. What I'm first doing is assigning a new variable named health, and I'm just going to set it equal to the original data. And the reason I do this is I'm going to manipulate the health variable, and I don't want to manipulate my original data. Next, what I'm going to do is for all of the values of health that are equal to 1, I'm going to set that to be good or better. So I'm going to change all the 1s to good/better. For everything else, in other words, anything greater than 1, I'm just going to set that to other. So you had some other status other than good, better. And I'm going to do the exact same thing for the flu data, except if you're equal to 1, I'm going to set it equal to yes. If you're anything other than 1, I'm going to set it equal to other. And then this, right, this line of code we've seen before, this is going to create a contingency table of the health and the flu.vac variables that are objects that I just created. So if we run this, and then, so we've created this object table, we can actually just highlight table, or if you want to, down below we can type it in and highlight it. If we run this, notice here is all of that data summarized in that 2x2 contingency table. So now to perform the hypothesis test, all we have to do is run chi-square.test and then give it the table. And you'll notice here it's still using that continuity correction that we looked at earlier. And again, you can argue to leave that or to take it off. And we find our p-value here. So going back to my document, here's that output with the necessary piece highlighted. Again, I'm going to make a data note here to say, hey, this is what I'm using as my complement or my other group. And then at my conclusion here, I've got at the 5% significance level, we have enough evidence to conclude that a person's health status is not independent of whether or not they receive a flu vaccine. Now going back to our code here, another option that I could have had, instead of doing yes and other or good and other, what I could have done is just focused on the yeses and the nos for flu and the good and the poor for health status. So again, to do this, I would need to create my contingency table. So this time I did something very similar to what I did before. I start out by setting health 2 equal to my original data, and then I'm going to manipulate health 2. So health 2, everything that's a 1, I'm going to say good or better. Everything that's a 2, fair or poor. And everything else, if they refuse to answer, they said they didn't know, I'm going to set that to be missing. So this way, health 2 is only going to be comprised of good, better, fair, poor, or missing. And then I'm going to do the exact same thing with flu-vac, and I'm going to call it flu-vac 2. And then I'm going to create a contingency table. So if we run this, notice that for table 2, our numbers are going to be slightly different because everybody that refused to answer or didn't know, I set those to be missing. So now my comparison is just between the yeses and the nos and the good and the good and poor. This is also completely valid to analyze the data this way. The important part is the documentation. You have to say, hey, this is what I considered, or this is how I analyze this data. And then we could perform the chi-square test on table 2, and we'll notice our results were still statistically significant in this case. Now, to perform a chi-square test where you have, nominal variables with more than 2 levels, you do the exact same thing that you did here. You would still build the contingency table the same way. The only difference is instead of 2 levels, you'll have 3 or 4 or 5 levels, just depending on what you're looking at. But the actual code is pretty much exactly the same. So as always, this is enough to get you started. As you work with your individual data sets, there's going to be different issues that arise or different things that you want to do. So feel free to ask me, and I'm more than happy to help you with your code.